Hi, my name is Reza Rockney, and I'm a Google Cloud Developer Advocate specializing with Apache Beam. And with me today, we have Robert.
Hi, I'm Robert Crow. I'm a developer engineer with the TensorfLow group, focusing on TFX and production ML.
Okay, so today, Robert and I are going to cover doing machine learning inference with Apache Beam using a utility from TensorFlow Extended. If you go to the next slide, please. So we're going to do an overview of RunInference, which is the API from TFX. We're going to use a toy model that's learned its 5 times table to do this, and we're going to put this into an Apache Beam pipeline. We are then going to start doing things that you would need to do in production to make use of the pipeline. So pre and post processing of the data, followed by some more advanced uses of Apache Beam, because we can do things like branching and sequential inference with multiple pipelines, all within the same Beam construct. And of course, that's runnable both in batch and streaming. And then finally, we're going to finish off with some TFX component development. So next slide, please. And with that, over to Robert.
So when you're doing machine learning, it naturally falls into a series of tasks. And these tasks are familiar to anyone doing machine learning. You're going to start with ingesting your data, then you're going to validate it, make sure that there's not issues with it. Then you'll do some feature engineering to transform it in ways that make it train better, including things like doing embeddings for vocabularies to establish semantic spaces of text data. Then you're going to train your model, which is, of course, sort of the heart of the whole thing. And after you're training it, you need to validate it, make sure that the results are good. And if they're good, then you might push it to a production infrastructure if you're using your model for production. And then you're going to serve it. So these are mirrored in the TFX structure, or really any pipeline that you work with. And the way it works in TFX is we have a series of libraries that are used to then create components. And these are sort of the canonical hello world components that you start with when you just do a plain install of TFX. So I'm not going to go into great detail of these. We have other talks where we talk about each of these in some detail if you're interested. But for today, I just wanted to introduce the idea of the pipeline and how it maps to the tasks that you're going to perform. So one of the things about TFX that's important, really important, is that it runs just about anywhere. And how does it do that? Well, it runs it'll run on different execution environments, including in a notebook, if you're using a Colab, or just on your laptop, or you could also just be running in a Jupyter Notebooks environment or Jupyter Lab, in a containerized environment using Kubernetes, and of course on cloud using Vertex AI. You can also use it with different orchestration engines, including just pure Python in what we call the interactive context, or Apache Airflow is very popular, of course, and so is Kubeflow. And in terms of processing, you can actually perform the processing either on a single system like your laptop, or in a cluster using something like Spark or Flink, which is, of course, near and dear to our hearts. Or, of course, on the cloud, we have Dataflow. So having that portability becomes important because we want to meet the user's needs instead of requiring them to meet our needs. And it also enables users to move between different environments very easily. So I could be on the shuttle, for example, running things on my laptop while I'm doing development, and then when I get to the office, move that whole thing up to a cluster, and suddenly I have much more powerful infrastructure available to me, and I've made really only probably one change to my code, like a one-line change. And to some extent, you can also use different languages too by containerizing your components, and then as long as you maintain the contract for input and output, you could be running Java or Rust or whatever in your component. And this is important, in some cases for different teams or business units, especially if you've had acquisitions where people have come in and they've already been running things, and you don't want to force them to suddenly, move to a different infrastructure or language or what have you. So the portability part of this is important, and Beam really enables that. This is the Hello World TFX pipeline, a little different view of it. I want you to notice there's two types of components here. The components in orange are a training pipeline. So they're going to ingest training data, and at the end of the day, they're going to produce a trained model. The components in green are an inference pipeline. So they're going to ingest inference requests, unlabeled data, and they're going to produce predictions from that using a trained model. And that's the bulk inference component there. So the bulk infer looks like this. It's a fairly simple component. It allows you to you can batch things together and run inference. And you're going to run that inference using a Beam pipeline on a distributed framework like Flink. So this is another way you can leverage Flink for both your training pipeline and for your inference pipeline. We're going to be talking a lot about inference today in a little different way that becomes very important. So the bulk infer and RunInference work together. What is RunInference? Well, TFX components run data processing in Beam pipelines, or they can run it on a single node too if it's just a small amount of processing. Bulk infer runs inference using Beam and using a transformation called RunInference, which is going to take a trained model and produce predictions. So the RunInference transformation is included in the TensorfLow tfx-dsl library, and it can be used just in pure Beam, which is what we'll be looking at today. And Beam pipelines can be used with no TFX. So if you don't need the rest of TFX, you can just stand up a Beam pipeline. Beam pipelines can also be used inside TFX, both in the canonical components that we just looked at, but also custom components. So you can create your own components and do amazing things using Beam pipelines in a single component in a TFX pipeline. All right, so and with that, let me turn it over to Reza, and he'll talk more about Beam.
And so we're going to very quickly do a high-level overview. Obviously, we don't have time to get in depth. But one of the things I really like about Apache Beam's vision is to allow developers to use the programming language of their choice, Java, Python, SQL, Go, and to be able to use that language to build expressive pipelines using all the primitives that are necessary, and to then be able to run that on the runner of their choice. Obviously, today we're going to be concentrating on Apache Flink. If you go to the next slide, please. So what we have in terms of the components, we have our SDK, so that's Java or Python there. You describe your pipeline, which becomes a directed acyclic graph of computation, the DAG. So that DAG is then pushed to the runner, in this case Apache Flink, for the processing to actually be done. Next slide, please. And one of the really cool new features of Apache Beam, so in that previous slide, we had the whole graph being described in a specific language. So for example, Python. But with multi-language support with Apache Beam, you can actually have specific transforms each use a different language. So you can have a pipeline that is a construction of various Java transforms as well as Python transforms, all embedded within the same pipeline for example, in a streaming environment. Next slide, please, Robert. And of course, this ability allows you to build pipelines directly, or it allows folks like the TensorFlow extended folks to make use of Beam to build out their components as a set of libraries. So these are all things built on top of those Beam primitives that allows you to then run it on the runner of your choice. And of course, you can then mix and match things, as we are going to be doing with RunInference, where your code is going to be used for pre and post processing, but you use RunInference for taking care of the inference pieces. Next slide, please, Robert. And to do this, we're going to use a very simple model, which, as I'm not an ML expert, I'll let Robert describe.
Well, so this is just going to be a simple linear model. It's going to model a linear function. So we we have an intercept and a slope, which is essentially the same thing as a weight or a bias and a weight, and it maps a line.
Next slide, Rob.
So what can you do with a model? Well, you can do a lot of things with a model, but imagine trying to do these things without a model. So could you write a Flink pipeline, for example, to do speech to text? That would be a challenge. Could you do, a pipeline to do text to customer sentiment, and so forth? So you start to get the point here. There's a lot of things, a lot of power that you get by including a model in a Flink pipeline as a transformation that allows you to run inference. So those are the kinds of things that you would be able to do. Now today we're just doing this simple linear function, but there's a ton of different things that you could do with a model, and we're showing you how to use a model in your pipeline. All right. So this is our simple linear model. This is based on Keras. We're using the Keras API, and we have an input layer that ingests our data, which is very simple. It's one value. We have a dense layer with one neuron because that's all we need. And then we compile the model and we can generate a summary of it. So again, very simple.
Okay. So in terms of RunInference, and if you could build out the slide, please, Robert. Yeah. So the interesting thing about this is that, you could, within the user-defined code, which we call a do-fun with Apache Beam, you could actually build out your own code for doing prediction with the TensorFlow model. So you could just call .predict and get things done. But the reason you'd want to use RunInference, I think, is similar to the reasons Robert's described where you want to use TensorFlow extended for the ML operations. It's around productionization. So not only getting things running where you get a quick predict, but also being able to do this in a production environment where you want everything to be stable, to be able to scale out, and to do this with as little technical debt as possible. So obviously you could build all of these things yourself, but you'd want to hand this off to someone like the TensorFlow extended team who've done all this with the RunInference. So for example, one of the first things that you'll start thinking about is whether you need to batch inputs to the model for efficiency's sake, or ensuring you have a well-known output from the model. In this case, RunInference has a predict log that is a well-known proto that then other teams can easily use without you having to transfer that information. Key forwarding, so keeping metadata about the thing that you're predicting and having that pass through to the post-prediction stage, which we'll talk about in the demo. Doing remote or local mode. So local mode is where we, with RunInference, you load the model within the workers and it does the inference locally. Remotely with so things like Vertex AI on Google Cloud, you can make a remote call to the model where you wouldn't, if you didn't want to host the model locally in your Flink cluster. And of course, we do other things like if a model is loaded within a worker, it's shared across various threads. So again, all of these things are things that you would end up building if you started to do the prediction by hand, that the RunInference takes care of. And of course, you also get the benefit of anything else the TensorFlow extended team adds in the future. Next slide, please. So thinking about this in terms of RunInference, as we mentioned, we're gonna be doing the demo in the local mode. And what we're gonna be doing there is we need all of the workers to have access to the model. So we're going to store the model in a global location, a Google Cloud Object Store, Google Cloud Storage, which allows all of the workers to be able to get access. And the nice thing about Beam is it understands the different schemas. So depending on where the file is, there's no extra work on you to actually be able to pull that file in. Next slide. And the other thing that we're going to do during the demo is try and get it closer to production. So you will always end up doing some sort of pre-processing on your data. So data doesn't always come perfectly ready. There are things that you need to do in terms of feature extraction or simply reading from various sources. You may want to read from a unbounded and a bounded source and do some denormalization where you generate the features ready for the model. So we want to be doing all of that pre-processing. We can do all of that within the transforms that exist within the Beam pipeline before you get to the RunInference stage. Next slide, please. So one other thing that we'll be doing, that model that we have, that first layer actually just takes a float 32. But TensorFlow Extended Emma, when it does things, it actually produces TF examples in the intermediate stages for good reason. And we are going to do the same, again, trying to get this as close to a more production environment. So rather than just sending floats, we're going to serialize them in this well-known format. Next slide, please, Robert. And that is as tf.examples. Which is commonly used with TensorFlow. And these tf.examples are going to be serialized and live within a TF record, which is just a container that contains the examples, and that is then sent to the model. In order to make this possible, to change what we read in the model, which was currently a float 32, to understand a serialized string, which comes from this TF example, what we're going to make use of, if you, next slide, press tab, please, is a tf.function. So this is more of an advanced use of models, and it goes into signatures. And basically, with this signature, we can have a function that converts the serialized format into the start of the first layer. Again, we're trying to make this as close to a production environment as possible. And there are many more things you could do with signatures, but that's out of scope for this talk. But now I'm going to just move over to a notebook where I'm going to show you some of these things in a live environment.
So here we have a notebook, and we're going to run through the code on this. First of all, let's just have a look at the version of Apache Beam that we have installed. So we have 2.33. Next, we have that simple model that Robert described. It's got that single layer. And importantly, we have this input layer of float 32. And as we go through this, we'll show how we convert that to be able to take something else as a input layer, which is closer to what we'd get on a production system. The model summary we can see below. Next, we will train this model. Now, I've already done the training for this, and I used a data set which had data from 0 to 100 multiplied by 5, which gives us our 5 times table for it to learn from. Next, we start doing the prediction. Now, in this cell, the model we just can call predict, and if we were building a prediction system by hand in the do function, in the user-defined function in Beam, this is where we would start. The data that I'm going to get it to predict is this in-memory array for the number 20, 40, 60, and 90. And these are typed for float 32. So let's run the prediction. Okay, so our little toy model, it's a little learner, and it's done okay. It's managed to get pretty close to what needs to be the number for 5 times 20. Okay, so with the basics, I'm now going to save this model in a save model file. So what we're doing here is save model. This is going to save it to a location on Google Cloud Storage, as we want all workers to be able to get access to this. So here is the location that that file has been saved in. Now, a nice utility is safe model command line interface from TensorFlow. So if we, with this, I can actually introspect the model that I've created and have a little look inside of it. Okay, now the bit that's interesting here, and there's quite a lot of information, is this signature definition. So the serving default signature has got currently a type of float, and this is corresponding to the float that we see in that first layer. So in order to get this into more of a production format, we now need to do probably the most complicated bit of the whole coding exercise, which is this TF function, that advanced signature function that Robert was talking about. Essentially, what we are doing here in this function is we're going to take a serialized TF example and convert that to the type that is required for the model. With that, I'm just going to run that cell. And basically, the save model will now take that signature within it and let's save the model again. Okay. So the save model was done here, and let's show the model again, sorry. And in the output we see here, signature definition server default is now DT string. So this is now a serialized string that the model will expect, and that function will convert it to what the input layer needs. Okay, so next up, we're going to run a little bit of prediction and do our first Beam pipeline. Now, rather than that in-memory prediction numbers, we're going to use a TF record file. So let me just run that. Thank you. And we see that on the file system, we have a TF record. That TF record contains a serialized format of the numbers that we want to predict. Next, we're going to build our Beam pipeline. So with Beam, we have our pipeline object. And this particular utility from TensorFlow Extended is a nice helper utility for reading TF record files, which I'm going to use within the pipeline. Now, for those not familiar with Beam, the way that we construct the pipeline is we're going to take our pipeline objects, and then the pipe symbol essentially means apply. So we are going to apply this source. So we're going to read from TF record files, which gives us serialized TF examples. We're then going to pass it to our API, the RunInference API. And the RunInference API takes a bit of configuration. In local mode, essentially all we need to do is pass it the location that we've stored our model file in. Next, I'm just going to do a print. So I'm going to take the P collection, the parallel collection of elements that is generated from this RunInference, and apply the map print function. Okay, so we see our output. We've actually got back a predict log from our RunInference. And in that predict log is the information around the input. So what was input? This string, this serialized string, which in this case would correspond to 20, given our response was 99. So now this is all done with a simple output. Obviously, within a production system, you then want to take that output and do some post-processing with it. So we're going to take this predict log and start extracting the information that we need and get it ready for the next layer, which is often business logic. Now, just to show that in a straightforward way in this demo, what I'm going to do is convert that prediction log into a nice string for our print statement. Now, to do that, the pipeline is essentially the same, with the exception that we now apply the predict processor do function to our the P collection that the RunInference generates. And in terms of the prediction processor, what we have is this process function. We can see the type that is sent into that do fun, which is a predict log. And then we extract things like the input value, the output value, and construct a nice string. Okay, so I'm going to just quickly run this. And we can see the input, so the thing that we want inference done against, was 20, and the output was 99.99. Okay, so now we have a system that takes a single value and produces the inference. But in most production systems, we need some metadata about that inference, and we need access to that metadata in the post-production. So I'm just going to go to some slides to describe this. Here we have what we've done right now, which is having that value and then the value and prediction coming out. But if you imagine that value was an image, and we had the prediction of the image that this image contains a bicycle. We need some metadata, in other words, what the image name was, for example, or what the ID was in our post-processing to associate the prediction to something that's useful in the business realm. Another example of this would be an IoT device. So the sensor value for which, let's say, is temperature, we need to associate that temperature with the sensor. So the sensor ID needs to be a key that is passed in to the value. So essentially what we want to do is we want to pass in a key value and have key value plus prediction be accessible after the RunInference. And RunInference has actually got a bunch of nice options for input, so we can send in just the bytes like we just did, or an example. Sorry, we can send in bytes or an example like we just did. We can also send in tuples of key bytes, and there's quite a few of these signatures which make our life easier in terms of coding because we don't have to do so much conversion. So let's go back now to our notebook. And to make it a little bit more like a production system, what I'm going to do is, rather than use TF record files, which contain our predictions, I'm going to create a pop quiz within a data warehouse. So I'm going to use Google Cloud BigQuery as a data warehouse to store a key value pairs that we're interested in. The key in this case is going to be the question. So first question, second question, third question, etc., and the values that we'd like predictions for our little toy model to do in its pop quiz. In order to change our pipeline to be able to read from BigQuery rather than a file, what we need to do is just make use of one of Apache Beam's IOs, which in this case is the BigQuery IO. And there are many IOs available with Apache Beam for lots of a variety of sources. So we just change that line that we had before from TF record to read from BigQuery. This is going to pull the information. And then the next step is we need to get that information in the same format that we had in our TF record file. So here we do a mapping function against that data, which essentially creates a tuple of key and the serialized data that we need to send. We don't need to make any changes to RunInference because it just accepts this new format. And for the prediction post-processing, we now have access to a key. So we're going to use a different function. Here we're going to use prediction with key processor. And the values going into this now have changed from just a prediction log to be a tuple of bytes and prediction log. Again, we're going to do some extraction of input and outputs and print out some nice strings. Okay, so I'm going to just run that. This will take a few more seconds as it's now going to go and get the information from BigQuery from that table. It has extracted the pop quiz, and here we have our results. So key is fourth question, input is the value that was the question, and the output is our result. So our little model is doing okay in its pop quiz. Up until this point, we're actually doing a very serialized pipeline. So we have an input, we have some pre-processing, we have the inference, and then we have post-processing. But one of the wonderful things about doing this in Apache Beam is that we can actually create quite complicated graphs, directed acyclic graphs of computation, the pipeline object, and use multiple models within it. And for that, I'm just going to pass over to Robert to talk about some of the possibilities that this opens up.
So one of the things that becomes important in a production environment is the idea of live experimentation, because model metrics are not usually exact matches for the business objectives. They're things you can measure, but they often don't map exactly to what the business wants. So for example, in a recommender system, you can train the model on clicks because that's something you can measure. But what the business really wants is to maximize profit. So different products have different profit margins, and a click on one is not the same as a click on another. So there is live experimentation that happens in production environments to try to really move closer to your business objectives. And one of the typical ways of doing this is A/B testing, where you'll train more than one model, and then users are divided into two groups in some way. There's a lot of different ways to do that. And then they're randomly routed to one of the two models, and you try to gather the business results from using each of those models. This becomes a pretty standard way of doing testing. There's other ways too. So what we're going to do today is to work with multiple models in our pipeline to show this kind of live experimentation workflow.
Thanks, Robert. And so what we're going to do is we're going to just make some minor modifications to the code that we had before. And as well as that 5 times table model, we're going to add the 10 times table model to the flow using the same raw data.
Okay, so we're back in our notebook. And what I'm going to do is just modify that previous example to now be able to do multiple models against the same data set. So in order to do that, I am still reading from BigQuery for our pop quiz, but this time I'm going to put that into the P collection questions, which I'm going to use multiple times. So by simply assigning it the P collection to questions, I can then do questions apply. So in this case, I am applying the multiply by 5 and loading that into the P collection multiple 5. And I do again against that questions apply, which does the second model against the multiply 10. So now I have two P collections which contain our information. In order to bring all those together, I pass them as a tuple to the flatten operation, which was given to multiple P collections with the same element types, brings it all into one P collection, which I'm then running into the post processor. So I'm just going to quickly run this. And that's going off, reading the pop quiz from BigQuery and going to give us two sets of outputs. So the first set of output for the fourth question with the 5 times table gives us our result here, but also at the same time, it's done the same thing for the 10 times table. Now, this is two models being run against the same P collection. Next, Robert will quickly talk about other options which we can do, which is sequential models, so being able to run models in sequence. So with that, over to Rob.
So since we do have more than one model that we're working with, let's take a look at some of the other ways that you can work with multiple models. One way that's very powerful is called a Cascade Ensemble, where we're feeding the result from one model into another model as its input. So for example, what we're showing here, where we have a language understanding model, that can be a fairly generic model. And it's the results from that, what it understands of the language, is used in a product recommender, which is very specific to your particular business. So this is called a Cascade Ensemble. And if we look at a more complex Cascade Ensemble, we can do some really interesting things here. So for example, I could use a model to do speech to text using voice data. And then I could use text data with our language understanding and do sentiment analysis on that. Maybe I'm going to save that off to logs for understanding customer sentiment and customer satisfaction. And then I can use what I understand from that user in my product recommender. I can also use it in a support recommender, since they could be asking for a support problem that they're trying to, we don't really know what they're asking about. So it could be support or it could be a product. And then I need to give the user a response. So maybe I could give him a text response and then convert that to speech if we imagine this is happening maybe in a phone call. So here I'm using, 6 different models in an ensemble. And as we've seen, you can use multiple models in a Beam pipeline or a Flink pipeline. And this is an example of some more advanced way that you might be able to do that.
So for the sequential model, we're going to modify our pipeline again. And this time we're going to take the raw data, pass it to model A, and the output of that we're going to pass on to model B. And I actually use a little technique where I pass in some information with the key to that second model, so we can retain the original data that was produced. And with that, I'm going to move over to the notebook.
So we're now back in the notebook, and we're going to modify our example again to make use of a sequential model. So in the same way last time we had our questions P collection from BigQuery, we now are creating a P collection multiply. That P collection is then going to have the times 10 piece added to it. We also have a post-processing step after the questions, which allows us to take in that original value with that trick that I discussed around putting that original value with the key and getting that to come out at the end of the sequence. This allows us to hold on to that original question as we go through these various sequence of models. So when I run this now, again, it's going to go to BigQuery, get the pop quiz, run it through the first model, get those results, and then run the results through the second model, retaining our original key. So fourth question here, we see the original input, the output from the first stage, and the output into the second stage. Up until now, we've been doing all of this in a notebook. So I just wanted to show you doing this on the Flink Runner. So this is the Apache Beam website. If we go to Documentation and Runners and choose Apache Flink, we can see the various options for running the Flink Runner. I'm going to run with embedded mode, which will actually spin up an embedded cluster, pass the work to it, and give me the results back. So all I need to do that is pass in runner equals Flink. And for that, I'm going to go to the command line. So here we have a file, RunInference. This contains that final cell that we had before, which is the multiply along with the sequential calling of the next step. And I am going to run the Python command, which includes runner equals Flink Runner. So when I run this, it's going to set up that local environment for me. It's then going to send it the job, and we're going to get our results back. So while it does that, and my apologies for using a green screen, showing my age, but I do like them. So here we have our questions, fourth question, and the same output that we saw before. Okay, great. So with that, I'm going to now pass on to Robert, who's going to talk about more advanced component development with TensorFlow Extended.
So as I mentioned before, you can author your own components within a TFX pipeline to do a lot of the things that we've talked about today using a Beam or Flink pipeline, as well as other things that are more ML-centric and things that aren't ML-centric. Maybe they're just part of your production infrastructure or your workflow. So things like alerting your security team when you see issues. To do authoring of components, there are three styles for doing that. There's the easiest one, which is a Python function. You can also use a container image or what we call full custom. So I'm going to go through each of these really quickly just to give you a flavor for what authoring components is like. For a Python function component, you just decorate a Python function with a decorator that says, it's an @component decorator. And then you use annotations on the function signature to identify input and output artifacts and parameters to the function, as well as an output dictionary. And then from there, it's just Python. So very easy to write. For a container-based component, it's very much like working in a Docker file. You're going to create a definition of your component, including what image to start with, the command to start the code that you're going to run inside your component, and again, some input and output artifacts. And you're going to wrap all that in a Python call, just to define that component from the TFX side of things. For a fully custom component, you're going to write this in Python, and it begins with a spec of the component itself, which is, again, the parameters, inputs, and outputs. And then you write a class, which inherits from executor class. Now, it could actually, often does, inherit from other executors that are pre-existing. So if you're just going to take a pre-existing component and extend it, then this is the way to do that, because you can use Python inheritance to do an extension of a previously existing component, and then you don't have to write everything from scratch. And that's our talk. If you want more information, here's a lot of great links, including Apache Beam and a lot of information on TFX. So on behalf of myself and Reza, thanks for coming.